Now let's start and continue how to build a MikeShe model with the live demo. This is also separated into two parts. In contrast to the live demonstration where we started with the QGIS preprocessing and then turned over to MikeShe, for this recording we decided to change the order. We will now start with the more exciting stuff in MikeShe. And if you then want to follow also the complete workflow of how to build a MikeShe or how to pre-process the data for MikeShe accordingly in QGIS, you can also watch the second part. Now, as with every numerical model, before you start building it, you should always go through the conceptual considerations and ask yourself, if you want to build now a MikeShe model for your MODFLOW or FEFLOW model, is the groundwater model domain sufficient, big enough, or is it missing substantial surface catchments? Now, you need to consider sometimes groundwater models are delineated based on hydrogeological units, and they exclude by purpose, for example, hard rock areas outside of the actual aquifer because they do not really need to be considered for simulating groundwater heads. But these can contribute significantly to focused recharge zones along the valley edges. So if you want to build a MikeShe model in order to produce recharge, maybe even including 2D overland, you should consider to extend the MikeShe model domain way beyond the groundwater model domain. Now, you need to also consider where are the depths to groundwater less than 2 meters or 6 feet, because there you have potentially capillary rise and potential feedbacks from the groundwater. As long as you do not have a fully bilateral coupling, like you would have it here when you use MikeShe together with groundwater models like MODFLOW or FEFLOW, there are some processes that could be underestimated. For example, if you have a high groundwater table in the valley area, and then it would trigger higher evapotranspiration rates in the summer. This indeed would be a negative flux for the aquifer, so it would lower the groundwater and hence the ET would be lowered also subsequently. This process can be a little bit underestimated. If you want to have the full bilateral coupling, you should consider also turning on the 3D groundwater module in MikeShe and build also your groundwater model in MikeShe. Then do you need to include or can you neglect 2D overland flow, rivers and irrigation? This basically depends, of course, on your catchment characteristics. And you also need to consider how many time steps you want to produce and with which temporal resolution with your MikeShe. So how long will be your simulation period? Couple of months, 2 or 10 years? What should be the resolution then of your groundwater recharge input? If you simulate only a couple of months in MODFLOW or FEFLOW, you can use a daily output. If you want to simulate 1 to 2 years, maybe you should go for a weekly. And if you want to simulate 5 or 10 years or more, you should go at least probably for a monthly time step to keep the data file size in a way that can be handled by the softwares. Now let's start with the actual modeling workflow. Let's assume we have pre-processed the data accordingly, like we will do this later on together. Again, you will see here the data package that you will be delivered after the webinar together with the recording. In the QGIS, I normally store my GIS projects, in this case based on QGIS. And we will now, before we do the pre-processing, go through the MikeShe model. I give you here also a bunch of folders already, which are supposed to benefit or support a more streamlined workflow. But for you, important is the model setups folder. In here, you have the inputs, which we have. We assume we have to pre-process. We have pre-processed them already with different folders according to the modules. And then here are the actual models organized. Now let's start here with a new model. I open here a Mike0 session. This is the platform on which MikeShe is based. And we create a new MikeShe file. I copy the path because the first thing you should always do is save the model. We always call it model she, quite simple, because this helps you a lot to automatize the post-processing. a lot because it always refers to the same naming. Now let's start with the MyShi graphical user interface. You always have here several buttons, pre-processing, which is a different process from the water movement and the water quality. They normally are run in a sequence. You can also press the play button. This will execute always pre-processing and water movement at least. You have here the option to load in shapefiles that can help you for the orientation. You can change here between image, grid, shape. You can even include here the river file or wells. Now in this case, I would like to at least display directly my model domain. You will see that you find this under the folder MyShi model setups input and domain. Then we have already something for our orientation. You can also use background maps. You can visualize the grid, which is I think not needed right now. And then we come to the simulation specification. Here you have different modules, and what we do now, we turn off the saturated zone. The nice thing with MyShi is you can see here this module tree changes depending on which checkboxes I hit. So you can run with a very simple model, then it would require only a domain, a topography, and at least climatic inputs. You see here no overland flow. If I turn that on, it appears again. Now for this demo, we want to use the 2-layer. And you can also see for each module you have different options. Subcatchment based is a more kinematic routing approach, and this is a real finite difference approach for the overland flow. So you can always choose based on your data data availability and your project requirements between more simple and more complex approaches. For the unsaturated zone, which is the soil model, we have 3 options actually. The most sophisticated and recommended one is the Richards. And we have the gravity flow, which is the Richards equation, so solving really the full soil water pressure curve. And gravity flow here is only a gravity-driven version of the Richards equation where capillary rise is neglected. And we have a very simple 2-layer unsaturated zone module. This is the one with which we will start. I will show you then later how the results differ to the Richards equation, which we will also prepare and discuss this quickly. Now let's start with the 2-layer method. We also take here the evapotranspiration, and we take the more simple approach Christensen and Jensen, which gives quite good results already. We also have here a more complex and physics-based SWOT approach, but it takes more data, so we will not cover that today. Now you can define a model domain as a DFS raster file or a shapefile. We recommend to use here the shapefile because then you are flexible in your model resolution, which would be fixed in the DFS input. Now it always gives you NX and NYY. You can change here the model resolution and extend. Now for the moment, we go for a coarse resolution like 100 meter. And then is always recommended to round here, like we will also do it later in QGIS in the pre-processing, at least to 100th, the origin of the model. You can see that this box is always changing a little bit depending on what I type in here. So what you do here, you really actually control the mask and extent of the internal grids that will be produced, even if you have only within the red area, which is defined by the model domain active cells, you will always create rectangular rasters with this DFS2 outputs. So it is recommended to, for the moment, cover here or make that as narrow as possible. So then your data outputs will be smaller and you do not need to create unnecessary data. So this looks quite good, nearly rectangular. By the way, you can always change the cell resolution and the discretization before each run, which is nice because you can change and adapt your model based on the needs that turn out during the modeling process. Now, the good thing is once you have done all the pre-processing in QGIS and the MyShi toolboxes where you don't even require a license, clicking together the model in the graphical user interface that guides you nicely through the process is quite easy. So you always change here, choose the spatial distribution, If you have organized it also in that way, which I highly recommend you simply take the folder that you have prepared, select the DEM. I have the correct item type, so this works, and I have my DEM already loaded in. Now for the climate, today I will not include snowmelt. I will only go for the precipitation. I change it to uniform, but I would like to have a time series. You can also use sub-areas of fully distributed grids, especially if you want to use radar-based data or satellite images, Earth observation data. Now in this case, I take a time series and then navigate to climate and precipitation and take the prepared precipitation time series. And then I do the same for the potential reference evapotranspiration, which is normally calculated with the Penman-Monteith. Now in this case, it tells me, which is nice, that the data period in this file is not sufficient. I know now that I, for this example, want to run the simulation from 1st of January 2010 to 2020. So you can always, before each run, also change the simulation period. If your data inputs cover sufficient amount of the period, you can always change this, which is quite nice, especially during the calibration process. Now in this case, I know that this simulation period here matches my validation period for this input file. I would always recommend you also to visually inspect the values. So for strong rain events, something between 40 and 80 millimeters per day is reasonable. And also a reference evapotranspiration for North Germany going nearly to zero in the winter months and not going beyond 10 millimeters is also realistic. You see also if something is missing. For example, let's change this here already to sub-areas. It gives you a red cross. And when you have a green arrow, that means you have provided to the model everything that it needs. Now in this case, yes, you have also various options here for the land use and the vegetation. I will choose, of course, sub-areas because I want to give a little bit of complexity to this test model. I will choose here the grid codes, and then I need my vegetation distribution file, which I find here, of course, under land use, vegetation, and I take here the land use grid codes. And then it automatically creates me here a drop-down. For each grid code now, I get here a zone where I can apply the values as I need them. Now I need to directly turn on. Well, let's do the first one together. Now it's up to you during the pre-processing, which you will see later. You need to know what grid code stands for which file. You can assign now the leaf area index time series and root depth time series individually, but the most common approach, we use a vegetation property file. Such a vegetation property file, you will find this also all under the input. You get that from us. We have prepared such standardized in evapotranspiration or land use database for you. So you can use this one under the folder ETV. This is a standard database that we use normally in European projects, and it contains the most important categories that are relevant for such a recharge model. And for each of them, you get here a kind of this temporal distribution based on the calendar date of the year, the date of the year, and distribution for the leaf area index and the root, and also a KC factor, which you can use to adjust further the parameters. Now, water and no vegetation, these are the transpiration relevant parameters. You don't have them. And if you go, for example, to forest, coniferous, you can actually see here changing values. We also have included some of the irrigation, important crops. And you see that normally if you try to match and align your land use distribution grids, for example, Corine, like we will do it later together in QGIS, try to match these ones, then you can directly use our files. But of course, it's up to you to create here new crop types or whatever you want and configure them individually as you like. Now, in this case, I know that for one, we normally take bare land. So there is no vegetation. I take a vegetation property file, create here a new entry, because you can also change them. If you have a land use change scenario, for example, you can change from non-vegetation to grasslands, or if deforestation is part of your project, you can take the forest values until a certain year, and then you change it to grasslands or bushes or shrubs. You see now here it recognizes that I have values from the beginning, but since no recycling is activated, it's missing here the values. If you click here, entire scheme, the model is happy. Now you can do this for all the other codes. I will jump over that because I have a model ready, so you don't need to watch me clicking that. So we go to the overland. We take the Manning roughness that we have pre-processed already in QGIS. I go to the overland flow, Manning, and we have our Manning roughnesses. Detention storage can be used if you have small sinks in your topography and you would to kind of include this process. We normally use this to take this as 0. If you have lakes, it can be recommended to also give it an initial water depth. Since we start here from scratch, we leave this as 0. Now, for the 2-layer method, some of these options are grayed out. You don't need them. We will need them later if we do the Richards approach. Now, in this case, for the 2-layer method here, you always need to provide the model these values: water content at saturation, water content at field capacity at wilting point, and the saturated hydraulic conductivity. Now, in this case, we have prepared already a soil map as polygons. I select them here and load them as a shapefile. Then Mike Shi is again giving me for each soil type the entry. Now, in this case, it's again a lot of work to enter these values manually, but we have taken away this burden from you. We will do this with a short HTML importer. I will show you. And you will find this under the pre-processing folder, Unsaturated Zone 2-layer and tools. So you have here an HTML update file. Here you can now choose. By the way, this is made by my colleague from Hungary, Zoltan Trabak. Quite nice and good guy to help me with these supportive tools. We go to Mike Shi model setups. We take our live model now. It will create a new Shi file. So it's detected the name. It's actually detected also already the grid codes that are set by Mike Shi. And now we go and take the database file that belongs to this shapefile here. You can also prepare it in Excel, XLS, or CSV. It will always look up the name of the grid code and will find the same name in the DBF. Then it's assumed that you have pre-processed the according fields, the 4 fields that you need in this DBF. You are then it's able to possible here to select the fields as you need them. Now in this case, water content at saturation, field capacity, we have it's recognizing already the correct values. And then you simply say update Shi file. Processing completed, updated user property records 145. Then you say download the updated Shi file. Now it asks you where to store it and also how you want to name it. Now in this case, we call it _updated, which is okay. We will also host this HTML. So you will get it anyway with the data delivery package with the recording, but we will pretty soon also host this HTML on our website for you. Now let's have a look how it looks like. That looks good. The values are inserted. Now in this case, I know this file This is kind of covering lakes, so there were no values in there provided. That's why for the moment I give this some dummy values to get it to run. Nope. Last one. Well, anyway, yeah, I can, now let's do it a different way. Then I tell you also another nice thing of this graphical user interface. So then you can also, you need to always apply or provide MikeShe with a groundwater table as lower U-set boundary condition. This is kind of the way it represents the saturated zone if you don't want to build the full 3D groundwater model. Now in this case, we derived that based on the official public available groundwater isolines. So we move here to saturated zone and levels, and we find here a grid, which we can use as spatial distribution of the lower groundwater table. Now we basically have everything that we need to get this small test model to run. And to show you the error message, I will change this one here to uniform now. Leave it for the moment as it is, and then you click pre-processing. And then it's already telling you that there are some problems. Now in this case, the georeferenced input files are not allowed when the model grid is non-UTM, which is good because this gives you a kind of gatekeeping option and prevents you from doing the wrong things. Now here you see pre-processing succeeded. That's good. You can always inspect also the files, how it is resampled to the new model resolution in here. Now it does not even give me an error message because I inserted already dummy values. You see this two-layer method, it's running quite fast. For 10 years, it takes only less than 2 minutes. But now let's go to the more, you can also always pause here, by the way, a simulation and continue it later. You can change a little bit also the CPU prioritization. Now in this case, I stop it because I have another model setup where we included the correct ETV files already for you. You will also be able to open this file yourself and run it. Probably the results I will delete because they are quite huge. But now you have the same model with exactly the same inputs from 2010, in this case to the end of 2019. And here now I already inserted all the ETV files with the correct time series. I actually ran this through. I also inserted here some stations, one with a high depth to groundwater, one with a low depth to groundwater. And I always show you now the time series together, so you can decide yourself if you want to insert here a new plot or if you want to have them together in one. If you want to create new, this is kind of the monitoring stations, the virtual monitoring stations. You could also give it the USET content. And give it the water content, for example, in the root zone. Decide if it should be a new plot or if it should be combined with the previous items. You can type in here the coordinates yourself, or you can click here, left click, and navigate to where this time series should be created. You can also include observation data. You normally do this when you have a full saturated zone module coupled. Then you include your groundwater monitoring stations here and include the observed data, and then you can navigate here to the field. Now we delete this one again. I have created here 2 pairs of outputs representing 2 possible monitoring stations, which you can see here. You can also change here the display settings. Now in this case, the high depth to groundwater gives you this kind of values. It looks like that. The 2-layer method, as I said, is a little bit more simplified. So you see not the full precipitation is percolating downwards and detected as recharge because we have a little bit of evapotranspiration, so it always takes the precipitation minus ET and the rest percolates downwards. This water then, the precipitation fills up the two-layer method, depending on the field capacity, and then ET takes water out of the two-layer method. If it is becoming close to a wilting point, you see that the actual ET is now going down, which is nice, and you would have no recharge here. So this is a quite powerful and efficient tool, but it's not giving you the best, let's say, most sophisticated recharge rates. The most sophisticated results you will get when you construct the Richards model. Now, how would it look like if I open again the demo model? So you can also change here now to the Richards. And the Richard, it works a little bit different. Here you can decide on your hydrogeological conceptual model which soil type you want to apply until which depth. So for example, in this case, I make it easy. I have from 0 to 1 meter below ground, from 1 to 2, from 2 to 3 different soils. Here you need soil property files. We have also for you prepared a dataset which is based on the USDA and the Unsaturated database. Now you see here the official ones. We use here ones there where we tweaked a little bit the parameters to be numerically more stable. And there you can select then the typical soil classifications. Such a UZS file, which is needed for the gravity and the Richards approach, looks like that. You can double click on that with Mic 0 and open this soil editor. Again, like for the ETV file, you can create here new soils and parameterize them if you want. In this case, you have this datasets predefined. And if you click on loam, you always see here the retention curve following Van Genuchten and the conductivity curve. You can enter here the values and really see how the soil moisture retention curve looks like, also how like the hydraulic conductivity here evolves. We have this now already inserted into our model. Oh no, we do it here now. So I say here I have clay at the top. Then I have maybe loamy sand, and then I have sand. Then you add here a numerical discretization. It's always recommended to have a finite discretization at the beginning because then you have stronger dynamics, but then you can increase here the numerical discretization. Now in this case, you can make this one 5, 2, 3, like that. And you should always try to consider that the depth is touching the simulated, the applied groundwater table. If not, it will throw an error. But now let's look directly into the results of the Richards approach. And this is actually where the great benefit of Mike Xi comes into the game. The Richards approach really solves the full 1D Richards for each soil column. You have the same model setup now. I have here this soil map mashed up in the reference scale 1 to 200,000. I have entered here already my peat, silt, soil, and the corresponding soil settings. I have here numerical discretization and here linked it to my soil data. I have chosen exactly the same location, nearly like for the two-layer method. And if I look now here, you can see with the high depth to groundwater, the recharge is quite low because there's a low conductive material in this area and it takes a long time. And you see this long buffered here hydrograph. If you go to the very end and you zoom here to the lower parts, You can see here a little bit the dynamics. And this is also that it takes here, you have kind of this hot start period. It takes 1 to 2 years until the first water drop reaches the groundwater table. We have here a depth to groundwater of 30 to 40 meters. So also this travel time is well represented. And then you always, so now we have looked at the results directly within one cell with this time series plots. But we can have now look also at the gridded outputs here. It's the total recharge to saturated zone, what you are interested in. These outputs are not automatically produced per default. That means under the storing of results, you need to check the total recharge to saturated zone. You see here all the items can be checked or unchecked. The grayed out ones are the ones that are essential for the water balance. Now, in this case, we produced here these grids. You can look them directly here inside the GUI. I change here directly the coloring with a predefined color palette to get again a more intuitive coloring here. Now these are the results of the 2-layer unsaturated zone method, and you see here they are quite homogeneous within a soil type. Because here it's a 2-layer method, it's very simplified. So you do not see these such nice patterns like we did it in the first session, but it can be already sufficient depending on your use case. Now, what we recommend is really to go for the results of the Richards, even if the simulation takes a little bit more time. The outputs are way more what we would like to see. So you see here a little bit coarser resolution in order to have a faster model here for the live demo. But you see here how the changes between saturation and drying out changes depending on where the rivers and the valleys are, depending on soil type, and depending also on the depth to the groundwater. Within this nice result viewer, you can also make time series plots. This will produce basically the same outputs like we saw this in the time series datasets. Now here again, you have this 1 year hot start run. It takes 1 year until the first rain gets into the equilibrium state. You see here such a high depth to groundwater that the highest groundwater rates are even detected in the mid of the summer, because even if the rainfall is coming mainly from the winter months, it takes a couple of months until it reaches the deep groundwater table. We can also go into more dynamic regions, for example here. Here you can see the typical groundwater hydrograph dynamics. Again, we have the warm-up period, and then it rises in the winter and starts to fall always into the summer. If we go into a region where we have even sometimes negative values, for example here, we have way more dynamics in the recharge rates, and they even become here as the zero line negative in the summer, because the low depth to groundwater triggers capillary rise and groundwater can evaporate to the atmosphere. Of course, you have then also stronger peaks because the percolation process is not that time lagged. So yeah, you see here these nice patterns you can produce with MikeG only with a couple of clicks and a couple of minutes to hours of runtime. Now, even this looks very nice and is very useful. If you want to plausibilize the outputs, you can create a so-called water balance file. This is also under MikeG. Here is a water balance calculation file. It's WBL. I will not go into the details because how to use that is explained in detail in the other webinar, in a recorded webinar on focusing on the water balance. But this enables you to create such nice water balance chart outputs. And I created now 2 water balances, one for the 2-layer method and one for the Richards. So I prepared them already beforehand. We normally have here an analysis folder at the same level of the SHE file, and in WBL we find here a water balance normalized for 1 year. So you have here the mean value for 1 year. The 2-layer method I ran for 10 years. The Richards I ran for 5 years. That's why you will see that even the precipitation averaged to 1 year differs a little bit because you have a different hydrology. If it would be the same simulation period, the values would be exactly the same. And we can see here for each chart output, for each water balance output, water balance item, how much in millimeters per year is flowing. So you have 760 precipitation, 390 ET, and nearly the half of it is here detected as groundwater recharge because we miss here the capillary rise. And on the right side, you can see the more sophisticated Richards values where only 234 millimeters of recharge are produced and 506 are evaporating, so slightly more because you have around 110 millimeters of loss due to capillary rise in this model. Now that's it with the Mike SHE results for today. And we continue now with the pre-processing workflow in QGIS. Thank you very much for attending.